All right, for Unit 7, Day 1, we're going to be talking about how to graph an exponential function, as well as how to answer some exponential application questions. So let me go ahead and go into, let me get my marker. All right, so first of all, for an exponential function, this is what they're going to look like. All right, typically the functions that we've seen before that involve exponents have looked like y equals x squared or y equals x cubed. When we usually think of exponents, we usually think of numbers to be exponents. But when we're talking about an exponential function, it's going to be swapped. Exponential functions have numbers as the base and variables as the exponent. So we're kind of swapping the job of what we would normally see when we're talking about exponents. So that's what you'll notice all of these equations look like. You have the variable, the x, is going to be in the exponent position, whereas the number is now going to be the base. So you should see that through all of these examples that we're going to be working with on this day. So this is your kind of generic form of the equation. You have your AHK that serve the exact same purpose as we've normally seen. A is always at the very front, and that's your stretch, compress, or reflect. Your H is always with X. Anytime you guys have an equation, it doesn't matter what the setup is, whether it's a root or an exponent or a quadratic, it doesn't really matter. The number that's associated with x is going to be grouped together with x. That's h, just like normal, and then k, again, just like normal, is all by itself at the very end of the function. So they serve the same purpose. Your h tells you left versus right. You just have to think opposite of what you would normally think. And your k tells you up versus down, just like it has in the past. Now the b in the function here, the b is not a transformation. The b is part of the function. So this part, like right here, the b in, well, I went a little bit too far, but the b and the x, those are always going to be constant for this particular parent function that's working in this generic setup. So the b is not a transformation, it's just whatever the base is, and x will just be x. It's the a, h, and k they're going to be swapping out when you have different parent functions for these examples. So exponential functions are actually going to have multiple parent functions that you're working with for each base. So because the base can change, you could have a base of 1, a base of 2, base of 3, base of 1/2, base of 1/3. You have all sorts of different bases. So there's no one parent function. There's just a parent function for each base that you could possibly have. So what we're going to do is we're going to talk about two different types of exponential functions. We have a growth function and a decay function, and you figure out which is which based on the base. So this example is an example of a growth, an exponential growth. The base is 10, right? The base to the exponent is a 10, and so we know it's going to be a growth when your b is greater than 1. So if your base that you're looking at, whether it's 10 or 2 or 20 or 5 or whatever, as long as it's bigger than a 1, then this is going to be considered a growth, and your graph is going to make this kind of shape. It starts flat-ish, because you have an asymptote that we're going to talk about in a second. It starts flat, and then it rises to the right. And it doesn't have to be, it could be lowered a little bit, so it has the asymptote a little bit lower, but this is the general shape it's going to make. A decay, an exponential decay, is going to have a base that is between 0 and 1. So that means it's going to be some sort of small fraction or decimal. In this situation, the base is 1/4, because that's the number beneath the exponent. So the base is 1/4. Because that's between 0 and 1, this is going to be a decay. The shape of a decay looks like this. You're going to start up and then fall. So they're mirror images of each other. For a growth, you obviously grow, and for a decay, you fall from left to right. Okay? So determining whether it's a growth or a decay is really easy. You just look at the base, and knowing whether it's a growth or decay is going to help you out when you're trying to graph it, so you know what shape it should be making. And that's what we're going to talk about first. How do you graph these? So the first thing you want to start with is a good foundation on understanding what the graph should look like, what the picture should look like. So the first few things you want to look for is what are the transformations, what's the base, and based on that, is it a growth or a decay? That's going to kind of help you out in determining what the picture should look like. After that, we're going to actually draw the shape itself. It does have an asymptote. An exponential graph does have an asymptote. In Unit 6, we had horizontal and vertical asymptotes in the same graph. For this unit, we're going to have two separate types of graphs. We're going to have the exponential, which we're learning today, and then the logarithm, which we're learning on day 3. They split the asymptotes apart. So this graph is going to have the horizontal asymptote only. It's not going to have both. It's only going to have a horizontal asymptote. Excuse my handwriting while I write with a mouse. Alright, so it has a horizontal asymptote. That means that the vertical asymptote is going to be reserved for the logarithm graph, which is what we're going to learn on day 3. So this only has a horizontal asymptote, and remember the equation for that is y equals, because it's a horizontal, and then it's going to be y equals k. It's just like what we saw on the day 2 for Unit 6 when we were doing reciprocal graphs. The horizontal is y equals k, and the vertical is x equals h. We don't need to worry about the vertical for this one, though. Okay, so you're going to have your horizontal asymptote. You usually want to draw that first so you have your boundary set up. To get the rest of the graph, you're just going to use your calculator. You're going to type the equation into the calculator, hit second graph to use the table of values, and then just find as many integer points as you can, write them down, and plot them. So the actual graphing is not that bad. You just get to use your calculator. The analyzing of the picture can be a little bit tricky. Some parts are easy, some parts are not. So we're going to be finding intercepts, the x-intercept and y-intercept. The x-intercept is sometimes really easy. Sometimes you can see it. You'll have graphed it, and it'll be written in your table of values, or it'll be right there for you. That's the easier situation where it's already there. You found it already. There are some times where the x-intercept is a fraction or a decimal, so it's not going to show up in your table of values, because remember, the table of values is only going to give you the integer points. It's not going to give you decimals or fractions for the x's. So if it happens to be a fraction or a decimal for the x-intercept, you're going to have to use this method, which if you don't know what that is, I'll teach you. I'm going to show you guys the calculator and how to do that. But if your x-intercept is not a whole number, you're going to have to do this. And it's a little bit more complicated if you've never seen it before. But we'll talk about that in a little bit. Most often, it'll be on the graph and easy to find, but just in case you have those more tricky ones, I want to make sure you're able to do that. And then the y-intercept is easy every single time. You're just going to use the table. If you don't have it written down, you can go back into your calculator. Remember that the y-intercept is always 0, something. So if you're trying to find the y-intercept, you just go to the second graph table in your calculator, go to where x is equal to 0, and then write down the y value. It'll be right there in your calculator. So you can ignore this. That's a little bit more busy work. You can use that. It will always work. Plugging in 0 for x is the technical way of finding a y-intercept, and it will always work. But a shortcut you guys can use if you're a little short on time, or if you just have so much else going on that you'd rather just use the calculator, you would make sure your equation is typed in, go to the table of values, go to x equals 0, and then write that point. And I'll show you how to do that as well in the calculator once we get there. And then we also have to find end behavior. End behavior is a little bit weird for this one because it depends partially on the horizontal asymptote. Nope, that's a 0. Horizontal. There we go. But only partially. So when we were in Unit 6 talking about the end behavior, the last time we talked about end behavior, the horizontal asymptote is what defined both end behaviors, both on the left and the right, because it interrupted your graph as it was rising and falling. So if you want to go back to see what I'm talking about, go back to Unit 6, Day 2. When we talked about the end behavior, it was always the horizontal asymptote that interrupted our paths, either going up and down. But this one, it's only going to be half affected by the horizontal asymptote. And once you guys see the picture, you'll understand why. But it's a little bit odd how it only sometimes is affected by the horizontal and sometimes not. But when you guys have the visual, it'll make much more sense. Alright, so that's all that you guys are going to have to do. Graph the picture, find the intercepts, the domain and range, find the the end behavior, and all that stuff that you would have to find after the picture is drawn. Alright, so let's start at the very beginning. We're going to set our foundation by finding transformations, the base, and whether it's a growth or decay. So remember, the base is directly underneath the variable. So my base is going to be 2 here. Because that's bigger than 1, this is going to be a growth. So it's going to make that upward shape like this. Okay? What I like to do when I was in high school and I was working with these kinds of equations, I would always circle the number that I was going to be using for the asymptote so it stood out to me and I didn't forget to use it. So in this situation, for an exponential, the number you're going to use for the asymptote is always at the very end. Remember, it's k. Y equals k, and k is always at the very end by itself. So I like to circle that so it stands out, because we're going to use that in just a second after we finish the transformations. So remember, transformations are everything except for the base, right? There is no extra number in the front here. It'll be very apparent if there is one. That includes a negative. So a base can never be negative. It does have to be positive. So if you have a negative, that's not B, that's actually A. If you look over here, if you have a negative in front, that's actually A. This one doesn't have anything, so there's not going to be a stretch or reflect or compress. So I'm going to move on to the 3 here. This 3 is representing the H. H tells you left versus right. I have to think opposite of what I would expect. So because it's minus 3, that's really going to be a transformation of right 3. I'm going to be going to the right 3. All right. And then moving on to the negative 4, because that's k at the very, very end as your up versus down. Because it's subtraction, that's going to be a down. So this is going to be right 3, down 4. Again, the 2, the base itself is not a transformation. So you would not, oops, I was saying 2, so I wrote it down. Sorry, down 4. The 2 is the base. You don't need to use that as a transformation. It's the base. It's separate from the transformations. All right, now the asymptote. We were saving this right here to get to this point. The asymptote is y equals k. In this situation, it's negative 4. So the asymptote is y equals negative 4. I'm going to stop here and go ahead and graph this, because finding the rest of this is actually really helpful. It is helpful to have the graph or the picture before you do the rest of this. All right, so the asymptote is at negative 4, so I'm going to go ahead and graph that right here. Now to find the rest of the graph, we're going to go into our calculator and find some points. So I've done that. So I have my calculator here. I have all 3 of the examples written in. I'm only going to be working with the first one though, so I'm only going to have this highlighted. You want to type in your equation. Now if you look at the example, it has 2, and then it has x minus 3 in the exponent, and then the minus 4 level with the 2. So when you guys are entering this into the calculator, if you have more than one thing in the exponent, you need parentheses. So you should have 2 caret and then parentheses around the entire exponent, and then the minus 4 on the outside. Otherwise, the calculator is going to be confused about what's the exponent and what's not. Right? So once you type it in, so it looks like this, you're going to hit second graph, so we can go to the table of values, and those numbers are way too big. So you want to scroll through and find as many whole number points as you can that will fit on the graph. So the ones that I have in this one would be 6, 4, 5, 0, 4, negative 2, and 3, negative 3. If you keep going, they're all going to be decimals. Those are not helpful. So you're just going to take all of those points, and it's going to take me too long to write them down, so I want you guys to do that for me in this table of values right here. Just write down 6, 4, 5, 0, 4, negative 2, and 3, negative 3. Those should all go in this table of value here. So once you write them down, then you can go ahead and plot them on the graph, and that's how you're going to get the picture. So our first, oops, I lost it on my calculator. The first point that we had was 6, 4. So we go over to 6, 4. I know this graph is a little bit hard to read, but we have 6, 4, and then 5, 0, which is right here. And then we have 4, negative 2, 3, negative 3. And those are the only points that we were able to, was that it? Was it just those 4? 1, 2, 3, yep, just those 4. And then you would, since this is a growth shape, we already know what it looks like, the growth shape right there. You can go ahead and just trace alongside of the horizontal asymptote and then go up through those points, and you have your graph. Just as simple as that. Okay? And remember, we use the fact there's a growth to kind of figure out what the shape is. Make sure you don't cross the horizontal asymptote, you just go right along top of it. You don't cross through it or actually touch it. I know it's awfully close there, but you don't touch it or cross through it, just go alongside. Alright, so now that we've graphed it, we're going to go ahead and look at the rest of this to figure out what's going on with these points here. So the x-intercept, this is one of the simpler ones. The x-intercept is where it's crossing the x-axis. So if you look at the picture, I'm very clearly crossing the x-axis at 5, 0, and you've actually already written that down. So I have the x-intercept really easy. It was in the table, and it's on the picture. So remember, an x-intercept has a number here and a 0 here. As soon as you have that written down or you see it in the picture, that's your x-intercept. Now, a y-intercept is 0, comma something, all right? And that's going to be down here. We don't have an exact point of 0, anything. All right, but that does not mean that there's no y-intercept. It just means you have to go looking for it a little bit further in your calculator. So the fact that it's not showing up here as an integer point means that this is going to be a decimal. So you're going to go back into your calculator. You're going to go back into your calculator, and you're going to scroll to where x is 0, right here. Remember, a y-intercept is always x equals 0, something. So this is my y-intercept right here. All right, so you're just going to take that and write it down. So at 0, I'm going to round to negative 3.9. 0, negative 3.9. All right, that's how you use the table right here to find the y-intercept. If it's not an integer number, that's okay. You just have to go looking for it. Scroll to where x is 0, and then write down the point that you see. And that's all you have to do for finding the intercepts using your table. Now, the domain and range, we do have to be using the same rules that we've done in the past with domain and range. We're going to use both set builder and interval notation. So the domain, remember, that's in terms of x, so I want to know what's going on with the x values as we're going from the left and the right. So as we're going left, I'm clearly going to the left forever. As I'm going right, I'm going up, but I'm also going slightly to the right forever as well. So if you're going left and right forever, that's obviously all real numbers. So our domain for an exponential is actually always all real numbers, right? Because it's going in both directions forever. That will always be true for an exponential graph. So this is what your domain is going to be for the exponential graphs. The range, however, is in terms of y, and because of the asymptote, you are not going to be going both up and down forever. You're going to only go in one direction forever. In this example, I'm going up forever, but I'm not going down forever. I actually level out at the horizontal asymptote. So when you guys are writing the domain and range, or sorry, the range specifically here, because it's not all our numbers, we're going to do the same thing that we did before. You have to decide what inequality you're using. Am I going above the asymptote or below the asymptote? Well, in this situation, I'm very clearly above the asymptote, so that's going to indicate that this is a greater than symbol because I'm going above. But what is it that my graph is above? You need some sort of reference point. What number am I above? Well, you're not anywhere below the horizontal asymptote. So the lowest value that you guys have represented on the graph is the asymptote itself, which is -4. So to find the range, you always tell me what's the lowest point and are you going above or below that? What's the lowest and are you going above, or what's the highest and are you going below? So you just think about it that way in terms of y. And then the interval notation would be -4 to infinity. You are not going to use a bracket around the -4 because you are not including -4. Remember, there are no points along the asymptote. The asymptote is just like a reference or a boundary. So it should not be equal to -4. So that's why it's in parentheses. And that's your domain and range. These should not be new or foreign. We've analyzed domain and range for different kinds of graphs. It's the exact same rule. You just have to look at the picture and understand which inequality you're using. It's pretty straightforward as you're getting familiar with what these graphs look like. The end behavior is a little bit strange. The more you practice it, the more comfortable you'll be with it, but it does seem a little bit strange at first. So the end behavior, remember, this is the left side as x is approaching -infinity. So as you are going left on your graph, right, we're going in the left direction. Typically when we think about end behavior, we think up versus down. But we saw in Unit 6 situations where the asymptote interrupts your journey downwards or upwards, and so you would have to use the horizontal asymptote instead. That's what's happening on the left. All right, it looks like as I'm tracing this graph, I'm clearly falling, but then I stop falling and I level out as I'm going along the asymptote. So even though I'm falling, my end behavior is not -infinity because I can't actually get there because I can't go through the asymptote. So instead of saying -infinity, instead I'm just going to go ahead and write the lowest number that I'm reaching or leveling out at, which is -4. That's when your asymptote comes into play for the end behavior. So wherever you're leveling out, I'm just going to write leveling. Whichever side of the graph you're leveling out on, that's when you use the horizontal asymptote because you're neither going above well, it depends on the shape of your graph, but you're not going through the horizontal asymptote, so you're stopped right there. All right, so when you're leveling out, when you're flat, all right, you're going to be using the horizontal asymptote. On the right side of the graph, as I'm traveling to the right, clearly my graph is going up. There's nothing to stop its journey. There's no asymptote to interrupt its journey, so it will be going to +infinity on the right. So one part of your graph is going to be flat, in which case you use the horizontal asymptote, and then the other one's going to be pointing up or down, and you would use the appropriate infinity there. Okay, so I know it's a little bit weird, but you just have to look at the graph to understand what's going on. And if you guys get a question where they don't have a picture for you, remember, always use your calculator. It's a tool that you're going to have the entire time. So just make sure that if you don't have a picture, you always have it available. You just have to use your calculator to get that visual kind of guide to how to approach the question. All right, the next one here, let's go ahead and do the exact same process. I'm going to go a little bit faster through this one. So the base is 1/2, because that is the number directly underneath the variable. Because it's between 0 and 1, this is a decay, so it's going to make that falling shape like this. The transformations, oh, we got to circle that k, because we're going to use that in a little bit for the asymptote. The transformation does not include 1/2. There is no a, there's no extra number out here. There's no h either. There's nothing together with the x and the exponent. The only transformation I'm going to have is the -8 at the end. And because that's k, that's going to be up versus down. Because it's subtraction, it's actually going to be a down. So my graph is being shifted down 8. That's the only transformation. The horizontal asymptote, remember this is a horizontal asymptote for an exponential, so it's going to be y equals k. We've already circled k to make it stand out. So a horizontal asymptote is -8. As soon as I find that, I'm going to graph it so I don't forget that I'm supposed to graph it. All right, so I have that. And then you're going to go into your calculator again. You're going to pause on this. You're going to go ahead and graph the picture so it'll help us out to answer these questions. So back to our calculator. Oops. I'm going to unselect that. Where's my enter? There it is. Great, now I'm going to focus on this one. So this one had a fraction as a base, so you want to make sure you have the parentheses there. There was nothing in the exponent except for x, so you do not need parentheses there. Your calculator will be able to know that you want x in the exponent and -8 to be outside of the exponent because there were no parentheses around this expression. So only use parentheses in the exponent if there's more than one thing in the exponent there. So this is what it should look like. Then you're going to hit second graph. You're going to write down all the whole number points that will fit on your graph. So you're going to have -4, 8, -3, 0, -2, -4, -1, -6, and 0, -7. We're going to have 5 points. Nice points that we can work with in this situation. So again, you want to go ahead and write those points down. It's going to take me too much time and my handwriting is going to be horrible, so I'm not going to. But go ahead and write the points into your table of values so that they're easy to access. And then once you have those written, we're going to actually graph them. So we have -4. Oops, let me go ahead back into full screen. There we go. We have -4, 8, which is here. We have -1, oh, just kidding. We have -3, 0, which is right here. Oops, oh my goodness. We have -2, -4. We have -1, -6, and 0, -7. And remember, it makes that falling shape. So you're going to be tracing these points and then going, oops, I am on the horizontal asymptote because my mouse is a little bit messy, or it makes things messy. Just make sure you don't cross or go on top of the horizontal asymptote like I did. Just skim right along top of it. And you'll get that decay shape to your graph. All right, coming back to resume our analysis of this graph, what's the x-intercept? Where you can see very clearly both in your table of values and on the picture, the x-intercept is right here. That's -3, 0. All right. Thankfully, on this equation, the y-intercept actually is an integer point, so you actually have it written in here as well. Remember, the y-intercept is 0, something, and we actually have 0, -7 as one of our points. So I didn't have to go looking for it extra like I did over here because it was already an integer. So it was nice and ready for us on both the picture and the table of values. So those ones are nice and easy to find on your graph or table of values. The domain, remember, is all real numbers every time because it's going both left and right forever. So you want to make sure you use both notations. This is a kind of summarized set builder notation, so that's why I'm not doing the X bar, just so I can fit it because there's not a whole lot of room. Feel free to use that notation. I think they do that on the SOL as well, as long as you can recognize either form of that type of notation. All right, range. Again, this is where you guys are talking about y. Is y going above or below the asymptote, which is our kind of cutoff, our reference point for the range. So our asymptote is at -8, and my graph is very clearly above that. So if your asymptote is your reference, all right, I'm above that. So it's going to be y is greater than -8 because the horizontal asymptote was -8. So that means that my graph is from -8 to infinity. It's everything above that lowest point, right? For a range, you always read from the bottom up. So you want to start at the lowest point and go up from there. So the lowest point was the horizontal asymptote. That's why I'm using it as a reference. So I'm at -8 and everything above, but not including -8. So it's going to be -8 to infinity, like this. All right. Now the end behavior, remember x approaching -infinity, this little thing means the left. So on the left side of the graph, shoop, I'm going straight up. There's nothing in my path to stop me from getting to positive infinity, so my end behavior on the left is positive infinity. However, on the right, you'll notice that as I fall, I stop falling and I level out, and this is where I'm flat. When you guys level out or flatten your graph, your end behavior is the lowest you can get, which in this case is the horizontal asymptote, -8. So where you're flattening out, use the horizontal asymptote. When you're shooting straight up or straight down, use your infinity. That's the second example. All right, this third one here is a little bit of a brain teaser. So this one, the base is the 3, all right, because that's the number directly underneath the exponent. And I know that you guys will want to say that because the base is a 3, it's a growth. But in this situation, it's actually neither. So the reason why it's neither is because of the A in front, right? In the previous two examples, we didn't have anything in front of the base. In this one, we do. When your A is negative, it's going to reflect your graph, because that's what a negative A does as a transformation. It's going to reflect your graph, and so it's no longer going to be a growth or decay. A growth or decay needs to be above the horizontal asymptote. When you reflect it so it's underneath, it loses either of those properties. So we can't call it either one of those. All right, so go back to the transformations. That negative is a reflection. Right, and we're only going to have reflections across the x-axis for our purposes in this unit. The 2 is a separate transformation, so the negative is separate from the 2 when we're referring to transformations. So the negative does a reflection, the 2 does a stretch. Remember, we've talked about that in the past when you guys are working with transformations. So the negative is a reflection, the 2 is a stretch, the 3 is not a transformation because that's the base. There's no h because there's nothing with x, but there is a +4 at the end. That's your k. I'm going to go ahead and circle that for later. Your k is going to tell you up versus down because it's positive. It is up, so up 4. Now the horizontal asymptote I was looking for is going to be y equals k. K is 4. So your horizontal asymptote is +4. You can go ahead and graph that for us. Now because this is a reflection, it's going to be beneath our asymptote, so it's going to be down in here. In order to figure out exactly what the shape is, we're going to go to our calculator again. So you're going to go back to your calculator, and you're going to type in that next equation. So you have the -2, and then you have the 3 raised to the x in parentheses like it's presented in the equation, and then +4. And you're going to go ahead and go to second graph so you can see some points. All right, so those are not good. The only nice points we're going to be able to fit into the graph are 0, 2, and 1, -2. So only a couple points, but that will give us enough information to figure out what the shape will look like. And if you can't figure it out from those points, you can always actually hit just graph to see the shape, like this. So you know how to connect the points to get that shape. So if you're not sure what the shape should look like, you can always just hit graph to see what that shape is. But the only points I'm given are 0, 2, and 1, -2. 0, 2, and 1, -2, and then it makes that falling shape like this. Now I know it's falling, but we're not going to call it a decay because a decay has to be up here, and it's down here. So it doesn't really have any sort of title for this kind of exponential function. All right, let's go into the x-intercept, y-intercept business. Now, for the x-intercept, we've seen in the previous example that they're very clearly on the graph as integer points. We had them written down. They were really easy to see. They weren't fractions or decimals. They were really simple. This is an example where that's not happening. All right, the only exact points are here and here. The x-intercept is over here somewhere. It's a decimal of some sort. So we're going to have to do something different to figure that out. I'm going to show you in the calculator how to do that. That's the this thing I was telling you guys about. Some of you may know how to do it already, others may not, so just bear with me. So what you're going to do is you're going to go back here, right? You already have that entered, never mind. Go into graph. You need to hit regular graph so you guys can see the picture. You want to see the graph. Now what you're going to do is hit second trace. All right, that's why I wrote calc, because to get to calc you need to hit second trace when you're working with the graph. So you're going to see this screen and you're going to go to 2 because an x-intercept is a 0. Remember, 0, root, x-intercept, and solution all mean the same thing. So you're going to go to option 2, and this is what your screen's going to look like. It's going to have a little blinking cursor. I don't know where it's going to be. It could be in a different spot originally. You're going to have a little blinking cursor. It's going to say left bound question mark. Now what we're going to be doing is we're going to be narrowing a window for the calculator to look for the x-intercept. So we're going to tell the calculator what point is slightly left of the x-intercept. We can see it right here. Right? We just don't know exactly what that number is. We can see that it's right here. So using your left and right cursors, see how I'm moving the little, I'm moving the little blinking dot, right? I want to move it so it's right, it's right next to the x-intercept, but slightly left of it. This is going to be a little difficult for you guys to understand visually. Don't think above or below. That's going to mess you up. Don't think above or below. Think, oh, here's the x-intercept. I'm going to go slightly left of it. All right? That could be up. It could be down. It changes. So don't do up versus down. Think left versus right. We're trying to find the left bound. So I'm going to go slightly left of the x-intercept, which is over here. You can even go like a lot left if you want to. You want to go left and push enter. You've just told the calculator, I want you to start the window right here. Now it wants the right bound. So now you're going to go to the right of the x-intercept. If this is the x-intercept, if I keep going, I will be slightly right of the x-intercept. And then you push enter. So in your calculator, you have these 2 little things that you've set. Sometimes they even draw the lines physically. You've set a little tiny window around where you know the x-intercept is. So now the calculator is going to say guess. It wants permission to execute the operation. You push enter one more time, and it gives you the x-intercept. All right, so again, second trace, 2. Take your blinking cursor so it's slightly left of the x-intercept. Scroll so it's slightly right of the x-intercept. Push enter one more time, and it gives you the x-intercept. So this one's going to be 0.6, 0. All right, so the x-intercept is 0.6, 0. It's not as often that you have to do this process to find the x-intercept, but if it's a decimal that you can't visually determine what the number is, you have to use that process. The y-intercept again, the y-intercept is where it crosses the y-axis. We had that one. That one was nice. It was just 0, 2. Again, that one you don't have to do any sort of complicated mess like you did here. You can just go into the table of values and find it if you didn't have it graphed already. So 0, 2. That's all good. All right, domain really quickly is all real numbers, just like usual. Both notations. For the range, again, you want to think what's the lowest value, because we always read a graph from the bottom up. What's the lowest value, and then what's the highest value? My arrow here indicates that my graph is going to negative infinity. So my lowest value is actually negative infinity, and I'm rising to get to the horizontal asymptote. So my graph is below, it's underneath the horizontal asymptote. So because the horizontal asymptote is my reference point, and I'm underneath that, then it's going to be y is less than 4. Because my graph, the highest point is 4, and it's going down from there. You use the horizontal asymptote as a reference point, and it's below that, so it's y is less than 4. And whenever you have a less than, right, an underneath or below graph, you have to use the negative infinity first in the interval notation, and then the uppermost point as your second endpoint in the interval. So it goes from negative infinity up to 4, and that contains the entire graph. All right, so just be careful on whether it's above the horizontal or below the horizontal asymptote, and then I'll tell you which inequality to use. On the left side of my graph, right, as I'm going left, that's where I'm leveling out, so I have to use the horizontal asymptote there. But on the right side of my graph, I'm very clearly going straight down, so I get to use negative infinity for the end behavior there. All right, so this is one example of each of the types of graphs you guys will see. Some parts are easier than others. You just have to rely on the visual, and that should help you a lot when you guys are finding the details. Now on the SOL, obviously you can't graph anything by hand. It is multiple choice or TEI questions. So I want to show you guys how to approach these kinds of questions if you see them on the SOL. So there are two different types. They could give you a picture and ask you to match it to the equation like I've shown here, or they could give you an equation and ask you to match it to the picture. I haven't included that here because you guys hopefully should be able to figure that out. Based on the equation, you should know what the horizontal asymptote is, whether it's a growth or decay, and then how to find the points, exactly like we were doing over here. That's literally what we were doing. We were determining what the points are, what the horizontal asymptote is, what the picture should look like, and so that's what you would do for that kind of question. If they give you an equation and want the picture, just do that process that we just did and pick the answer choice that matches what you got. This is going the other way. I have the picture. I want to know what the equation was to begin with. So there's a three-step process, and you may not have to go through all of the 3 steps, but the way that you're going to analyze these equations to figure out which one it is you're going to check 3 things, at least 2 of them, sometimes 3. These are your kind of lifelines as you're verifying whether the equation works or not. The first thing you want to check is whether the graph is a growth or decay, because your answer choices are going to be a scattering of both growth and decay. If it's one and not the other, you can immediately cross out the answer choices that don't match. So for this one, because it's rising, this is clearly a growth, so I can automatically cancel this one out, because that's a decay, so that obviously can't be the answer. That's your first lifeline. The next lifeline that's going to help us cross out even more answer choices is what's the horizontal asymptote? Well, here they don't have it graphed, but you can see pretty obviously the horizontal asymptote's right here at +4. So this has the horizontal asymptote of +4, and so does this one, but this has a horizontal asymptote of -4, so that's not the answer choice. See, we're just going through and crossing out the ones that won't work. So we've used our 2 lifelines here. It's a growth with a specific horizontal asymptote, and now we have 2 options left. Is it the one where the base is a 2 or the one where the base is a 3? If you make it to the 3rd lifeline here, all you need to do is type each of these into your calculator one at a time, go to the second graph, and find which one of these has a table of values that has those 2 points in it. All right, this one and this one. You want to go into your calculator, enter this equation, right? Well, not that part. This part, you want to enter that into the equation using the parentheses and being very careful, and then go to second graph and see if it has -2, 5, and -1, 7 in the table of values. If you do, which I actually want you to do, and go verify this, but if you do, you would get the -2, 5, awesome, cool, but then you would get -1, 6. Alright, so that one didn't work because it didn't give me the -1, 7. If you type this into the calculator, you do get -2, 5 and -1, 7. So this is our answer choice. So that's how you work through these options to figure out which is which. Again, over here, you start with the first lifeline. This one is falling, so that's a decay. So I'm going to get rid of the 2 growth situations. The second lifeline is talking about the horizontal asymptote. This one's horizontal asymptote is right here along the axis, so that's an asymptote of 0. So that means that you should have a k of 0, which means there shouldn't be a k. Remember, when either h or k are 0, it means that those numbers are not present. This one has a k of 1. All right, so that's not it. This one doesn't have a k. That's a k of 0, so that means this is your answer choice. If you have something missing, if it's missing from where it should be, it means it was a 0. So that would be your equation to match this picture right here. Right, and that's how you would go through those questions to analyze which equation would work. I'm going to skip the domain range and end behavior for these because we already practiced them on the next page. You'll practice that more in the homework. Just make sure that you guys are on top of those topics for our quiz and test. All right, now I'm going to leave the graphing section. All right, that's all you guys need to know about the graphing of exponentials. Now I'm going to talk about the application questions. So this one we've actually worked with a lot already. It's another stat edit stat calc. We've already done stat edit stat calc 4, 5, 6, and 7 for a linear, quadratic, cubic, or quartic. And now we're going to add our fifth and last model in here, the exponential function. That's going to be stat calc 4. So if you want to write that down, it's calc, not 4, sorry, 0. I meant 0. To find the exponential model, it's going to be stat calc 0. And that's going to be the last type of model that we're going to be seeing. So I want you to go into your calculator, or you could just watch. I've already done it. So remember, anytime you guys have a table of values like they have here, they have this big, long table here with X's and Y's. You put the top one in list 1, and you put the bottom one in list 2, which I have done. Stat edit. I have all the points in here already. Now remember, you cannot jump to conclusions. When they give you a table of values, I know the directions here say determine the exponential model, so I already tell you it's exponential, but they won't always do that. They may just say find the curve of best fit. Very, very basic and very vague. So you are not going to know what shape this is unless you actually see the points. It could be linear, it could be quadratic, it could make the n shape of a cubic function, it could make the w shape of a quartic function. We don't know until we see the points. So that's where the zoom 9 comes in. Remember, I keep telling you guys, turn on plot 1, clear everything. Whenever you guys have plot 1 on, everything should be empty. Whenever you guys have something written here, plot 1 should be off. Okay, so it's like a switch. This is on, those need to be off. If these are on, that needs to be off. Okay, so turn plot 1 on and erase everything. Then you're going to hit zoom 9. All right, so now you can see these points. You can see they are gradually falling like this. That's an exponential decay graph here. So this does make the exponential curve. Typically, they are more distinct. They're a little bit more sharp of a fall. But this one, the directions told you it was exponential already, but if they don't tell you, the exponential shape will be much more specific or distinct. Right? So we know it's going to be an exponential model, and we can see that based on the points. Now, because we know it's exponential, now we've done stat edit, we're going to go to stat calc, and then we're going to go to 0. Should have gone the other way, it would have been faster. 0, expreg, exponential regression. And you're going to push enter until you see your screen here. Remember, an exponential has an a and then a base, and then the exponent is a variable. They don't worry about the h or k business. We're just going to use this right here. So what you're going to do is you're going to take the a and the b and plug them in, rounding to 3 decimal points, and you have your equation. So our equation here would be y equals 87.74. You don't need to write the 0. All right, it's a little bit redundant. And then 0.9, and I can't remember, 46. Sorry for my handwriting. Raised to the x, right? You just plug in a and b, and that is your model or equation. If they ask for one, that's what they're referring to. So that's the exponential model. Now the follow-up question says, based on the model, what was the initial temperature? Remember, initial means beginning or starting point, and when we're talking about data, that's always referring to when x is 0. It's where you started at the very beginning, so no time has passed, or the length is 0, or whatever context you're speaking within, it's always 0. You start at 0. So what you're going to do is just plug in a 0 for x. That's how you find the initial anything. You plug in 0 for x. So if I do that, and I'm going to let you do that in your calculator, but you'll find that you would get 87.74, because when you have an exponent of 0, anything to the 0th power is 1, so basically this cancels out, right? It turns into a 1. It would be this times 1, and so it's just that. Okay, so again, you can just let your calculator do that if you don't remember that exponential rule, but you'll get this answer either way. And then this one says, what's the predicted temperature after 1 hour? Notice in the table it says that the time is in terms of minutes, so I'm going to convert that hour into minutes. It's going to be 60, and so I'm going to do the exact same thing. Over here they wanted the initial temperature, which is when x was 0. Over here they want the temperature after 60 minutes. So I'm going to do the equation here. It's the same equation. It's just instead of x, I'm going to write 60 in the exponential position. So when you type that into your calculator, which I have not done, hold on, I have to remember the answer. 0.9646 raised to the 60. Oops. I had 2 left parentheses instead of 1 left, 1 right. I don't know why I did that. You should get 3.138. And that should make sense, right? This was an exponential decay, so you should notice that all of the temperatures are falling, so it should make sense that once you get like way past 34, like way out here, the number should be very small, right? Now I do need to warn you, I need to remind you guys, and I have mentioned this in the past, anytime you guys use a table to find an equation, once you've used these numbers to find this equation, they are completely off limits to answer follow-up questions. it asks for the initial temperature, and when you look back over here to where x was 0, it very clearly says 79, and that doesn't match this. But that's not a problem, right? Because see how it says based on the model? They wanted to know what the estimated value would be based on this equation, not what it actually was from the data. Anytime you guys find an equation, this is an estimation. It's not going to be perfect. It's not going to match exactly. It's an estimation of this data. So once you plug these into your calculator, forget them. Cross them out. You're not going to use them ever again. Never answer these questions by looking at the chart. It's always based on the data. So be careful you don't fall into that trap of going back here. It's very dangerous. The directions should say based on the model, but even if they don't, you still have to use the model, this equation. All right, so we've done that before, the stat calc stuff. I'm just showing you the new type of function with stat calc 0. All right, the last types of application questions you guys will see are going to be specific to exponential growth or decay, like in a word problem, or when you guys are working with something called continuous compounding, and this is with money. This could be with a population, potentially a cost or the worth of something in money. You're going to be able to tell very clearly which one of these two formulas to use. Again, this is going to be a word problem that's talking about a growth or a decay. This is going to have this wording specifically in the directions. If you see continuous compounding in the directions, you are going to be using this equation. We call it the PERT equation because that's what it spells, P-E-R-T, PERT. So if you hear me referring to that, I'm talking about this equation here. That is specifically used for this kind of situation. Any other time that you guys hear something about an exponential growth or decay of populations doubling or decreasing of value of something, that's going to be this. I don't have a fancy word for it, but it's P times 1. I actually don't like how I have this in the notes, so I'm going to rewrite it just so it's a little bit more applicable to our situation. I'm going to write 1 plus or minus r in parentheses raised to the t, and then I'm going to change this to this. It's okay the way it was written before, but I think it's easier to explain if I write it this way, so I want you guys to go ahead and change it. So this equation, the p for either of these is your initial amount. It's where you started. The r is the rate of growth. This should always be a decimal. So I'm not going to be able to fit the word very well, but if you guys could do me a favor, draw a little arrow to the r and write decimal. I'll just abbreviate it, dec. Right? The rate should always be a decimal, so they're almost always going to give it to you as a percent. So you need to take the percent and divide it by 100 to get the rate. And then if the rate is greater than 0, all right, if it's, I don't even know why it says that. It should be greater than 1 as well. So if your rate is greater than 1, specifically, then it's going to be a growth, obviously. We talked about that when we were graphing. And if your rate is between 0 and 1, so it's a small decimal or a fraction, it's going to be a decay. Now, I wrote the plus or minus up here. How do you know which one to use? Well, when it's a growth, you're going to be using the plus, and when it's a decay, you're going to be using the minus. It's pretty straightforward. So you just look at R to figure out whether you're growing or decreasing, or you use the directions, and then you use plus for a growth and minus for a decay. And then T is just going to be the time that they're referencing in the word problem. Right? All right, so let's go ahead and look at this one. This says the bacteria reproduce by dividing. I'm going to go ahead and go full screen now. All right, bacteria reproduce by dividing. When each bacterium in the population of bacteria divides, the population doubles. Important word there. The initial amount of bacteria in a petri dish was 25 bacterium, and it divides every hour. So one thing I want to make sure you guys are aware of, that is doubling is a 100% increase. If you go from 1 and then you double that, you go from 1 to 2. So that means you added another 1 on. And 1 is 100% of 1, right? If you go from 2 to 4, you added a 2. 2 is 100% of 2. So you're just adding 100% onto your original. So that's going to help us out when we're writing this equation. So we're going to write the function that models the situation first, and then we're going to solve this equation based on this specific time. So I'm going to use y instead of a sub t, because you guys, I feel like you're more comfortable with y. So y equals, and p is the initial. So they're telling us the initial was 25. So I'm going to plug that in, 25. Then I have 1. I need to stop for a second. Is this a growth or a decay? Well, I can see that when a bacterium divides, there becomes more of them. So the population is growing. Doubling means that it's increasing, it's growing. So it's going to be a plus. Now we need to figure out what the rate is. So we've already discussed that a doubling is a 100% increase. Well, this is a percent. If you turn it into a rate, that means you need to divide by 100. So if you take 100% and divide it by 100, you get 1. So the rate is 1, so that's going to go here in the position of the function. And then t, which we don't know yet, t is the variable like x would be, that would go here. So if you're neatening it up just a little bit, you would do 1 plus 1 is 2. This is the equation. That's the function, all right? Remember, we don't know t yet. T is what's going to change. That's the independent variable that you can put anything in there and it changes the answer. So that's why that's the only variable in the function. Now, based on that, we already have the equation now. We have y equals 25 times 2 to the t, power of t. That's the best way to say it. Now we want to use that expression to find the population after 10 hours, so all you have to do is they've given you t now. Before they hadn't given me t. For the follow-up question, they have. So you're going to do the same equation, 25 times 2, but instead of the variable t, we're going to use 10. So you just plug that into the calculator and see what it gives you. So 25 times 2 raised to the 10th power is 25,600. And that's all that you guys need to do for these questions. Use the wording to write the function, take the time that they give you, plug it in, and let your calculator do the work. That's all that's involved. This next one says that a new car depreciates in value 12.5% per year. The purchase price of the car was $35,000. Depreciates means that it's decreasing in value. That's what that word means, if you didn't know. So we're going to write an expression for this. So it's y equals the initial P, that was 35,000. 35,000, parentheses, 1. Now, because it's depreciating, remember, depreciate means that the value of the car is decreasing. So because this is an exponential decay now, we're going to go ahead and use a minus. When it's a decay, you use minus. They gave me this as a percent, so you have to remember to divide by 100. If I divide that by 100, I would get 0.125. And I'm going to go ahead and use n for this situation. They've specified that they want it to be n. You can leave it as t if you don't catch that, that's fine. But this one's specified as n. So just to neaten it up a little bit, inside the parentheses, it would be 35,000.875 raised to the n. So that's the equation that they were looking for. Then they follow up and say, what's the value of the car after 5 years? So you're going to go ahead and do the same equation. But now they specified what n they want. So you're, instead of writing n, oops, that's supposed to be a 5. Sorry about that. You're going to plug in a 5 right there, right, for n, because they gave you the time that has passed. So you would get, equals, oops, I used the wrong number, hold on. 0.875 raised to the 5. There we go. 17,951.81. Okay, so that's what you would do for that one. We have a couple more on this page that are a little bit different. So this one says the number of fish in a pond in 2011 was 580. In 2012, the next year, right, the population had increased to 667. If the trend continues and the fish are increasing exponentially, how many fish will be in the pond in 2020? So the first thing to notice is that we have increasing exponentially. So this is a growth. So I'm going to have y equals, the first number you're going to write is your initial value, which we're just going to start in 2011 because that's the first year that they mentioned. The initial value was 580. This 1 is always constant. That will always be a 1. This is subtraction, or sorry, plus. It should be a plus because it's a growth. Now we need to find the rate. I don't see a percent mentioned anywhere in here, so you have to do a little bit of work to find the rate. So what we do know in terms of the change like how it increased, is that from the first year it was 580, and then into the second year it became 667. So what we want to do is figure out how much is that increase, and then once you find the actual increase, what percent of the initial was that, and that's how you find the rate. So between these 2 years, the fish increased by 87, and the way that you find that is you take the bigger value and you subtract the initial, so the after minus the before, you subtract them, and that gives you how much the increase was. So from this year to this year, it increased by 87. Now 87 is not the rate. Dividing by 100 is not the rate. It's not 87 or 0.87. This just tells you how many more fish there were. To find the rate, you want to know how much of the initial is this. Did it increase by 5? Is this 5% of the 580? Is this 10% of the 580? That's how you guys figure out what the rate is. Okay? So the way that you do that is you take this number, the difference between the before and the after, or the difference between the after and the before. The order matters because it's not commutative. You're going to take that and divide it by the initial. And when you do that, you get 0.15. In this situation, you do not need to divide by 100 again. We've already done the appropriate work to get the actual rate here. So you would just type it in as 0.15. You do not do the extra divide by 100, because this is not technically a percent. They've written the percent as a decimal already when they do this work. All right, so that's how you find the rate if they don't provide it for you. You do after minus before, and then you take this and divide it by the initial value. And that's how you get the rate. And then we're just going to use t for time. And then we're going to go ahead and find the time, because they have provided that for us, but I'm going to go ahead and neaten inside of the parentheses first. So 580 and then 1.15. All right, now what's t? All right, they wanted us to find how many fish will be in the pond in 2020. So if the initial year was 2011 and they want us to go all the way to 2020, that means 9 years have passed. So that's the t. I know that's hidden a little bit in the wording, but you can find it. So if your year is 2020 and you started in 2011, you can subtract them, you get 9. 9 years have passed, so you would use 9 for t. So go ahead and plug that into your calculator. You're going to get 2040. We usually don't use decimals in these kinds of questions because you don't want to consider a part of a fish, right? It's like 0.3. You don't want to consider 0.3 of a fish, right? So we just use whole numbers when we're talking about populations like that. When they're talking about money or worth or things like that, you can use decimals. But typically when they're talking about living objects, we usually use whole numbers, right? This last one, the population of tigers in a certain area is decreasing at a rate of 0.8% per year. There are currently 800 tigers in the area. How many tigers will there be in 50 years? So the initial is right here. There are currently 800, so that means the initial is 800. This says very clearly in the directions that they are decreasing, so that's a decay, so I'm going to use a minus. This is the rate presented as a percent, so you need to divide that by 100. I know it's tricky because it looks like it's already been divided by 100 just because it's so small of a decimal, but don't let that fool you. It still has a percent, so you have to divide it even more, make it an even smaller decimal. So when you divide, it's going to become 0.008. All right, and then they already tell you very specifically the time is 50. So you don't even have to write the t as a stand-in. You can just automatically put it in and then stick that in your calculator. So 800, and then you do the 1 minus 0.008 raised to the 50, and you get 535. Again, don't use a decimal there. Yep, and then that would be that one. Alright, so those are the examples where you guys would use the first of the two formulas. This one, when you notice it's an exponential growth or decay situation. The next ones we're going to do, you can see very clearly, it keeps saying compounded continuously, compounded continuously, compounded continuously. This is where you guys use the PERT formula. If you see money, you see interest rates, you see compounded continually, that's when you would use the PERT formula. This one's even easier. There's no trickery to finding the information that you need for the formula. It's all going to be there. You just plug it in and go in your calculator. So the PERT formula spells out PERT. So you have A equals P times E raised to the R times T. E is a number just like pi. We're going to talk about this more on day 2. Just like pi represents 3.14, E represents 2.72 in your calculator. Rounded, of course. It keeps going. But E just represents a number. And so to find the E on your calculator, let me show you. The E is right here above the division. So to get an E to show up, you just push second, divide, and there's an E. Okay? Pretty simple. Alright, so for this one, find the value of $500 after 4 years invested at an annual interest rate of 9% compounded continuously. So the initial was 500. That's where the investment started. E is just a number, so it just stays E. And then it was a rate that's a percent, so you need to divide that by 100 to get the actual rate you're going to use in the function. So that's going to be 0.09. And then you're going to multiply that times 4, because that's the time. And you just stick this right into your calculator. 500 times E raised to the 0.09 times 4. You want to write it exactly as I have in your calculator. Put parentheses around both of these when you multiply them together. And you should get 716.66. Like that in your calculator. And that's really all there is to it. There's really no ambiguity in these questions. They give you everything you need. You just plug it in. So like for this one, the value that it started with was 4,000. You have your E. Then you go up into the exponent. Your rate was 4%, so it becomes 0.04. And then 3 years is how long they want you to be investing. So you would put all of that into your calculator. And you should get 4,509.99. And then the last one here, you have an investment of $1,000. And then you have your E with an investment rate of this percentage. As a rate, you have to divide by 100, so you would get 0.076. And then they want the yield after 8 years, so you would multiply that times 8. So it would be 1,836 times, 0.75. And that's it. So just look for the wording to tell whether you use the PERT formula or this one, and then you'll be good to go from there.